Okay. What were the announcements? Okay. Anyway, so I'll start I guess today's topics. So today we're going to continue with unsupervised learning. So today we're going to look at principal components, some clustering algorithms, and the clustering algorithms will include k-means, k-medioids algorithm, and spectral clustering. Okay, so what are the learning goals for today? So today we're gonna, so what is the main input for a clustering algorithm? It's not just the data points. Okay, it's also going to be how do you say one data point is similar to the other or dissimilar to the other. That's kind of more important. Actually, that's more important than the choice of algorithm actually. So you need to kind of completely internalize how do you say a data point is different from another data point, and that generally comes from domain knowledge. So it's not statistical, it's not data driven generally. So you have to use domain knowledge to differentiate two observations. Okay. The next part is going to be how does k-means work. So I'll write down, so the way we're going to discuss k-means is that there is going to be again an optimization view, in the sense that there is going to be some objective, and we want to optimize for that to figure out clusters. But it turns out that doing that optimization is hard, and so we'll take the easy route. I mean, it's not going to solve the original problem, so it's going to do something else in an iterative fashion, and that's how we're going to motivate k-means. Okay. It's very, so when you look at the k-means treatment today, you should be at the back of your mind, you should think about EM as well, from lecture 7 or 8, right? So EM also did something else, right? We couldn't maximize the likelihood of the data, so we hypothesized that each data point, for example, for mixture models, comes with a latent variable, unobserved variable, which tells you which component it belongs to, and then we did an EM style, iterative way to estimate parameters of the original problem. So there's a parallel there. The third goal is to understand principal components. So I think there was a part in lecture 4, I think, which was discussing a way to understand what ridge regression does. Like, what does it do with the data matrix that's in input? Okay, at least on the training data. How does having a ridge regression, that regularization penalty, how does it influence my estimation, my beta hat, and therefore my estimation, compared to not having that penalty? Okay, so the difference between the penalty could have been viewed from a principal components point of view. So today we'll try to see if we can get there. But in general, I'll motivate what principal components are. So hopefully by that section, you should know exactly what principal components are, principal component directions are, and what are they trying to capture. Okay, so they are keywords, but they're pretty simple. So if you've already seen the refresher course on linear algebra, there's this thing called SVD, or matrix factorization, and there are eigenvalues and eigenvectors. So I would suggest, if you are not familiar with them, after this lecture or after this class, just look at those couple of 20 minutes, 10 minutes of video, just to familiarize yourself with what are eigenvalues, what are eigenvectors. Okay, simple concepts. And the last part is going to be spectral clustering, which is going to do two things. It's going to use k-means. Okay, it's part of the algorithm is k-means, and part of the algorithm is using the notion of eigenvalues and eigenvectors. Okay, so that's why it's so we're going to start with clustering, then do dimensionality reduction or PCA, and then again get back to clustering. Okay, that's the objective today. Any questions about the lay of the land? No questions? Okay. So okay. So clustering is an unsupervised learning task, as I mentioned, and the objective is to understand your data. So the way you understand your data is you segment it, break it into parts, so you can understand each part better. And there are multiple ways to cluster. Okay, so the one way that I've already alluded to, I think in the last lecture, was this thing called Gaussian mixture models. Okay, So Gaussian mixture modeling is a statistical way, or I guess a probabilistic way of assuming something about the data and therefore breaking the data into parts or components, like 2 Gaussian components or 3 Gaussian components. Okay, so you've already seen Gaussian mixture models, how to estimate its parameters, and once you estimate its parameters for any new data point, you can see whether the data point is closest to which Gaussian center. So let's say there are 3 Gaussians in that mixture, then each will have its own mean values, and you can just ask how far is my new data point to each of the mean. Maybe it's closest to one of the means, and that's your cluster, or that's your component. Okay, so you already know how to do clustering using GMMs. Okay, so Gaussian mixture models already studied. But what we'll do today is a little bit of a less statistical approach, but it's still an approach to understand your data, which is going to be from, so this is, I guess, statistical. In a sense, it assumes something about P of X, right? So there's a specific, P of X is the marginal distribution of a joint distribution, which has Gaussians, multiple Gaussians and component probabilities, right? Today we're going to look at, let's say, a family, but like optimization point of view. So point of view. And under this we'll study several things, and let's start with k nearest neighbors and oh, not k nearest neighbor, sorry, k means, and k means and k medoids. Okay, and then we'll talk about one more algorithm later, spectral clustering. But let's start with this. But even to introduce k and understand k means and k medoids as ways to optimize, or to get to some clusters or segments, we need to first start with the essential component. Of course, the essential component is going to be the first component is going to be data. The second component is going to be similarity metric. Okay. And we've already seen when we studied k nearest neighbor, this was the same thing, same case, right? We had data. We also had to specify how, what is the meaning of neighborhood, which why would I call a point A an observation A and observation B neighbors of each other, right? If they were already in Euclidean space just means a bunch of real numbers, a vector space, right? With the distance measure being the Euclidean distance, just the sum of the squares of the differences across coordinates. We already kind of assume that as implicit, but you can change the metric. Okay, so if you have categorical data, maybe Euclidean distance doesn't make sense. You may want to use some other measure of differences between data observations. For example, if one observation is one feature is like whether it's cat or not, and the other feature is whether it's cat, and the other observation point has dog there. What's the difference between those coordinates? Is it cat minus dog, or is it like 1 minus 0, or is it something else? Okay, so you can have variations like that. And similarity metric now again is important for k means, so you have to specify that externally. Actually, for k means, it's kind of, we'll see in the treatment we assume Euclidean distance. Okay, but if you don't want to assume Euclidean distance, you can go with k medoids, and because it actually doesn't even need the metric definition. We'll see. Okay, I mean, it needs the metric definition specified, but with the metric definition and the data, you pre-process and get something which is essentially the similarity matrix, and only that is the input to the algorithm. Okay, so the algorithm just sees a matrix in this case. Okay, this sees a matrix which is n cross n, where n is the number of observations, okay, that you want to cluster, whereas this guy sees n cross p, the usual n observations, p coordinates, and it also sees the the Euclidean distance. Okay, this is the Euclidean distance. I mean, this is a 2 norm. Okay, Um, yeah. Okay. So let me give you a couple of examples of what similarity metrics are. One I just mentioned is the Euclidean. So the Euclidean distance is actually the opposite of a similarity metric in the sense that, if two points are far away in the vector space, then the distance is large. Okay, I mean, the distance being large is not saying that they are similar, but they are dissimilar. Okay, so you can flip the sign. So for example, so let me say, let's say if you had a dissimilarity metric. I mean, actually, I don't want to use the word metric, but let's say, metric means something in I guess analysis field of mathematics. But so let's say dissimilarity measure or some sort of a scoring function. Dissimilarity between points, xi and xj. Now these are p dimensions, right? So maybe they are in Rp, which is each coordinate is a real number. A real number. Then like one example could be just this, right? Sum over j is equal to 1 to p of xi j minus x. Oh, let me use k is equal to 1 to p of x I k minus x j k the whole square, right? So this is just an example. I mean, this everybody fine with this definition of a dissimilarity metric, and then you can convert it into a similarity by just saying, what are the ways in which you can convert it into a similarity metric? Any ideas? Any simple ideas? Like heuristic? Yeah. So this is a dissimilarity measure, right? Dissimilarity score. I want a similarity score. And if 2 points are far away, it's high. If 2 points are far away, it should be low because they are not similar. Yeah, just it could be negative, or it could be 1 minus, like 1 by that or something like that. Okay, 1 divided by that. Let me not put negative here, but let me put positive here. That's dissimilarity. And another example. So this is example, I guess example 1, and example 2 is the correlation. Okay, it's I'm just using this symbol rho. Just think of it like a p with a squiggly underscore there. So let's say my data matrix X, this is n cross p, right? So what I'm going to do is that pick a feature. Okay, this is the jth feature, jth column. I'm going to take the mean of those numbers. Let's say they're real valued, some level, some measurement, maybe pressure or something. They're all real valued. Take the mean and subtract it from every observation. Okay, that's I can do that pre-processing, right? I can subtract the mean from every observation, every column from its mean feature value. So once you do that, then the correlation function is written this way. J is equal to 1 to p. Actually, let me not use j. K is equal to 1 to p x I k x j k divided by, oops, let me not put this, rho is equal to of xi to j, where xi and xj are two, like let's say this is xi and this is xj. I don't want to use j here. Let's say it's some Lth feature. Okay. So two observations. This is just a definition of correlation. Okay. Just normalization. I mean, this is a definition of empirical correlation. Okay. Xi and xj are xi and xj are the rows. So yeah, so here so it's a difference between correlation between features, and I'm defining correlation between observations. So you can, I mean, any two vectors, okay, you can take the difference between them, like the Euclidean distance that I showed in the previous slide, just a pointwise difference between them, sum of squares, that's a measure of dissimilarity. Here I'm saying any two vectors, you can just do, multiply the entries, as long as, I mean, so there's a formal definition of correlation, right? You have to take x minus expectation of x, y minus expectation of y, divided by, square root of the variance or the standard deviation of x, the standard deviation of y. So same thing. I just removed the means by saying that for each row, for each column, I removed the mean value. So there is no expectation of x is 0. Okay, that's all.
So when exactly are you taking the correlation between xi and xj?
Yeah.
Shouldn't you also normalize it horizontally?
Oh, good question. So let me see. No, I mean no normalization horizontally. It's normalization, vertically. Okay.
It does make sense, right? Because
no, I mean,
when you do it,
what is meant by normalization horizontally?
So I'm just saying when you do the normalization, like correlation between features.
Yeah.
You normalize them like vertically, right? Because
It's same thing. We are doing the same. We are doing the same normalization in both operations. Okay.
All I'm saying is that both doing the vertical normalization, you like xi and xj will have different values, right?
Yeah. I mean, there are two observations. So okay, I think you're getting or we are confusing. I guess we are confusing ourselves between this. So why haven't I put an expected, expectation of xi and expectation of xj there? Okay, so let me actually not use this. So what was the definition of correlation? So it's just the expectation of x minus expectation of x. Sorry, expectation of this. I don't want to use y. Just use z minus expectation of z. Okay, divided by square root of the variance of x. Variance of z, I can expand, you know the definition of variance, right? Variance is nothing but, so variance of z is expectation of z minus expectation of z squared. Okay, so this is the definition, and we are just bringing it to data land. So that's why I said empirical correlations. If you're asking about features, yeah, I mean, so features are taking different values, so you're just asking for how aligned are they, how similar values do they take, okay, across observations. Okay, that's across n. There is a summation over n over there, whereas here I'm just taking summation over p's. Okay, so each observation is like each observation, think of that as like a p length p length bunch of numbers, right? That's what it is. So I'm just looking at how aligned they are. Okay, and for that I'm just defining the I'm just getting rid of this expectation of x as saying they are the same and they're 0. Okay, that's the only difference. Okay, so I'm just saying that each observation, think of it as like so each number okay, what's the right way to say this? Yeah, each number should be in expectation 0. Okay, each of the p numbers should in expectation be 0 is what I'm assuming. Yeah. Anyway, forget about the tangent. All I'm saying is this is a way to I mean, forget about the details, but this is a way to define again a relation between two observations. So all we're doing is saying two observations are similar or not. This is a way to say if this number is high, you can say that the two observations are similar, for example. Okay, and this number can be between -1 and 1. Okay, similar to this correlation, this actual statistical quantity below that I've written. So these are some ways to, and in fact, if these norms are Okay, in fact, if these two things in the denominator, if each observation is of norm is of the same magnitude, so these are called unit length vectors. Okay, their 2 norm is equal to 1, then the denominator each term is equal to 1, then the dissimilarity, the Euclidean distance is equal to 2 times this measure. Okay, so distance bit, let me write it this way. So xi minus xj 2 norm square is equal to 2 times 1 minus rho. Okay, if norm of xi is equal to 1 and norm of xj is equal to 1. Okay, remember these are points in our p. P, let's say, is 5 or something. Okay, all I'm saying is dissimilarity is negatively related to this correlation or similarity measure that we discussed. So he was saying that add a negative sign to change from dissimilarity to dissimilarity, right? So that's what's happening. So there's a negative sign in the front which made this similarity function equal to a dissimilarity function. That's all. Okay, any questions? No questions? Okay. So anyway, that was just a primer. So we have some intuition now about similarity functions. Now let's come to k-means algorithm. It's going to use so we're going to discuss what motivates the k-mean algorithm. Okay, what was the original objective, which is hard, and therefore we'll do k-means, and it's going to use one of the similarity measures. In fact, we're going to use this. Okay, the one the dissimilarity measure xi minus xj 2 norm square. Okay. So what is the objective? So the objective is what do we want to accomplish by clustering? Okay, for clustering we have n observations, right? Let's say 1 and n. For each of the points I want to say which cluster this belongs to. So there's a vector, there's a observation, p dimensional vector corresponding to each observation, and I just want to say let's say there are k, k in the name of k-means. So let's say there are k clusters that I want to visualize this data in. Okay, so I want to segment this data in. So I want to say, okay, point 1, does it belong to which of these k clusters? Okay, for point I, which of these k clusters, and for point n, which of these k clusters, right? So for maybe point 1 belongs to the kth cluster, maybe point I belongs to the first cluster, and maybe n belongs to the kth cluster. Okay, just an example. So for what we actually want to find through clustering is a function, okay, which given the observation index tells me which cluster it belongs to. So observation index is going from 1 to n, right? For observation 1 it belongs to cluster, in this example, k. For observation I, it belongs to cluster 1. Okay, so it's a function which maps from indices to indices. Okay, that's what we want. So let's call that function c, which goes from indices, okay, to indices. This is just a notation, I guess, but this is what I just said in English. So I just want a function which goes from given an index like observation 1, which cluster does it belong to? That's what I want. Okay, any clustering algorithm, any clustering approach should essentially boil down to this. Okay, and so the objective function, here's one objective function. You can have many ways to say what constitutes a good cluster of my bunch of points. Okay, so here's one example. So this is the scoring function for a cluster. So for a function c, which already tells me, okay, first point belongs to the k cluster, second point belongs to the first cluster, and so on. Given that scoring function, given that clustering function, c function, which maps indices to cluster indices, I can tell you how good that function is. That essentially is like how good my clustering is, right? Because your clustering is completely determined by the c function. Once you've defined the cluster, I'm telling you how good the cluster is, and that's going to be equal to, this is an example, but let's say this is an example function. So sum over k is equal to 1 to capital K. So we have k clusters, okay, capital K clusters. Sum over Ci is equal to k. Actually, the right way to write this is I such that Ci is equal to k, and sum over, let's call it j, such that Cj is equal to k, and some sort of a distance between them, xi, xj. Okay. All it's saying is, okay, I have k clusters. Pick the first cluster that already the C function tells me, right? Let's say the C function tells point 1, 2, and 5 are in the first cluster. So pick 1, 2, and 5. For 1, 2, and 5, look at their pairwise distances or dissimilarity measures and add them up. Okay, that's what it's saying. So this, for example, if 1, 2, and 5, these are the points which belong to the first cluster, then this would be this measure for the first person, for the k for the first cluster would be d12. I mean, I'm not writing x, but plus d25 plus d15. Okay, and actually 2 times that, so it also says d21 plus d52 plus d51. Okay, it's just a pairwise distances or dissimilarities, and that's why there's a 1/2. So I'm not taking into account, like exclude have an order relationship. That's why there's a 1/2. But don't worry about the 1/2. All it's the qualitatively what this is trying to capture is that if you've already given me a clustering assignment of points to clusters, then the way I'm going to measure the quality of the cluster is that I'm going to look at all the distances of points within a cluster, and if the pairwise distances between points within a cluster is I guess low, okay, so we want to minimize this. So if the pairwise distances between points within the cluster is low, then that the clustering assignment is good. Okay, that's it. That's the intuition. Any questions about the intuition? Okay, so given this, we want to minimize scoring, or what do we want to call it, scoring or C over all such assignments, cluster assignments, going from indices to cluster indices. Now this problem is computationally hard. Okay, because for each point there are k choices. Sorry, for each point there are k choices. So the n points. Okay, so there are n to the power k. There are k to the power n potential functions. Okay, in the sense you are searching for functions. These are cluster assignments. There are too many cluster assignments to consider. So you consider one cluster assignment, I'll tell you the score. Pick another cluster assignment, I'll tell you the score. There are too many such cluster assignments to consider. And these are somewhat discrete. They're not like I can do gradient descent and stuff like that. Things are, they are indices to indices, so I don't know how to kind of handle this. So that's what I mean by computationally hard, and you can make it formal. It's yeah. Yeah. No, distance is a positive, right? Euclidean distance. So 0 is the threshold. I mean, if all points are exactly on top of each other, then distance is 0. Yeah.
So you just compare the distances between all the other clusters.
Not so. So here's an example. So let's say 1, 2, and 5, right? And then I said, let's say what is the remaining 3, 4, and 6. Okay. So here I'm just saying that if the cluster assignment for this guy is 1 and this guy is 2, then if this is a candidate assignment, then I'm just saying the quality of this cluster assignment is this distance plus this distance plus this distance. That's all. And if I do some other assignment, right, I can okay, whatever, 1, 2, 5, 3, 4, and 6. Let me just put a bracket so that it's, yeah. So if I do another assignment like something like this, this is the first cluster and this is the second cluster, then this will have a different score, total score. So I mean, from the looks of it, this seems like a lower score version. So that's it. That's what we saw in the. But as the number of points are too many, there are too many such clustering assignments to consider. Okay, and so what we'll do is we'll deal with some other objective. Okay, so just like in the EM algorithm, the original marginal likelihood maximization was hard, so we introduced a different objective. Okay, so similarly here, what we're going to do is different objective. So what is that objective? Let me just call it scoring prime. Okay, now this is going to be a a function of C as well. I mean the cluster assignment, and it's going to be equal to sum over k is equal to 1 to k. Those are the number of clusters I have. Nk, which is the number of points in the cluster. The clustering assignment will split the points, right? So 3 points in first cluster, 3 points in second cluster. So Nk, for example, in this example is 3, 3. I mean for that C. Actually, maybe I should put a bracket C there, and then times sum over all the points I such that Ci is equal to k, okay, of xi minus x bar of k 2 square. Okay, so what is this capturing? It's saying that okay, the scoring for now a clustering assignment is pick each cluster that the assignment gives me. For each cluster, what is the number of points? That's like a weight. You know, if the cluster is large, then nk is large. Okay, that times every point in that cluster. Okay, how far is it? How far is it? That's this distance square. Okay, this is the distance square. How far is it from the center of that cluster? Okay, so x bar is Euclidean. What is it? X bar is just the average of the points in the cluster. Okay, so x bar for the cluster K is the average, which is just a sum over I such that Ci is equal to k 1 by nk of xi. Okay, it's just the average like this. Pick all the points in the cluster, just take the mean. So this is a slightly different function, right? I mean it's not, yeah.
So x bar is the same as the centroid then?
Centroid, I don't know.
Cluster?
Yeah, average of a bunch of points in the vector space. Is it called a centroid? Huh?
The average of their coordinate values.
Yeah, these are vectors, right? Just take a coordinate wise average of the numbers. Yes, I don't know, is that called a centroid?
Cluster, right?
Yeah, for the kth cluster. This is for the kth cluster. Similarly, if there are two clusters there, then x1 x1 bar, x2 bar. Yeah,
because I think on the homework we had to do a centroid.
it's called a centroid. Yeah.
How do you initialize this? Like,
No, I haven't told you. I just told you the objective now. I haven't told you the algorithm. We'll get to the algorithm soon. This is just objective. It's just like similar to the previous objective.
so
Okay.
you are saying that you kind of average the values of the point in the cluster, right?
No. Given C, I can compute this whole thing, right? Given C, I can find what are the points in the cluster. What's the mean point in that cluster? I can plug that in and compute the score of my full cluster assignment.
Yeah, but the C's will come after you kind of initiate the algorithm. Right?
We'll get to algorithm soon. Right now, I'm just scoring a given cluster assignment. Right? In the previous slide, previous page as well, I was just scoring a given cluster assignment. Right? I guess I call it scoring prime here, just to say this is a different measure.
Quality of.
Yeah, these are quality. So lower is better. Yeah. Any other question? Okay. Yeah. So that in general, okay. So let's see. Yeah. So this depends on C as well, right? So if I know the assignment, I can compute the x bar k, right? Because it depends on actually where is the Ci, the C of I here. So I mean this is also difficult to compute. Actually, this objective is computationally hard. Okay, but there is a way to break this problem so that we can at least do something greedy, as in something iterative. Okay, and we're going to do that by solving the I guess the relaxed scoring prime of that C. But now we're going to introduce additional variables called mk, one for each cluster. Okay, there's a collection of them. Mk are just those vectors. Instead of x bar k, I'm using mk because those are going to be now variables. Okay, and this is going to be the same objective as before. K is equal to 1 to the number of clusters nk times sum over I such that C of I is equal to k of xi minus mk 2 norm square. Okay, so this is called, I mean, so I just slightly changed it. Instead of x bar k, I call it mk, because I want to now make them variables. Previously, x bar k is completely determined once you give the cluster assignment, right? Here it's a variable, and the way I'm going to do this is first solve for. I'm going to do the following. First, given mk, solve for c, okay, and then given c, solve for mk. Okay, so this is going to be my core idea. I introduce new variables just like in the EM. You know, there was mu1, mu2. Let's say there's a Gaussian mixture model with 2 Gaussians. There was mu1, mu2, sigma 1, sigma 2. Okay, those are the 4 parameters that you are supposed to optimize. But I also introduced this additional hidden or variables or which kind of tagged along with each observation, which said which component belongs to the first component and second component. Here, similarly, these mk's are additional variables now. Okay, c is what we care about at the end of the day, but mk's are additional variables. I'm going to say fix mk, tell me what c could be. Fix c, tell me what mk could be. Okay, so given c, solving for mk is easy, right? If I tell you the cluster assignment, what could be mk is just the average of the points in the cluster. We just saw that, right, in the previous formula. But if I tell you what mk is, you can actually solve for a new c. I mean, you can solve for a c. If I just tell you mk's, okay, I didn't tell you where do each points belong to. I didn't tell you. If I just tell you what this mk values are for each cluster, let's say the 2 clusters, then I can check for every point whether it's closest to the first mk as m1 or is it close to second m2. Sorry, whether it's close to m1 or close to m2. If it's close to m1, just call c of that data point as the 1, cluster 1. And if it's close to m2, just call the c of that observation index 2. Okay, so that's easy, right? So given mk's, I can find the cluster assignments. Given cluster assignments, I can find the centers. Okay, the mk's, average of the points, right? So this is it. This is k-means. Okay, you just repeat this. So for loop for index, I guess, iteration, it's equal to 1 to, let's say, 1000, whatever number of iterations. Just run this. Okay, and hope is that at the end of the day you will have some stable c that will not kind of keep shifting. I mean, it will kind of localize onto having the cluster assignments being consistent across iterations. Okay, that's it. This is,
How do you actually determine the optimum number of clusters here?
how do you find? So the question is, how do you find the optimum number of clusters? First of all, this is I guess I'm going to start from extreme basics, but this is a unsupervised learning problem, so there's no objective measure. So if you feel after you see the clusters, if you feel that that's not enough, then you increase the number of clusters that you're going to consider. I mean, so there are many ad hoc, I would say, many heuristic ways to choose the number of clusters. I mean, there is a way, which I think some of you might have seen in 572, which is you look at a plot of k versus a score, or some sort of quality score was quality of the cluster, which like this relaxed score, versus a k, and you see some inflection point where, so as you increase k, as you have more clusters, your quality score should be going lower and lower. Okay, I mean, it's not should be going lower and lower. Lower is better. Okay, so if k is equal to n, each point is in its own cluster. Okay, then it's 0. Right, each point is in its own cluster. There's no error. I mean, there's no difference. There's no distance to consider here. Okay, so that's 0. When all points are in the one cluster, then there's going to be high score because there's no clustering you did. So in between, there's going to be some monotonic decrease. Okay, and you will see where there's a large drop, after which there is not much large drop, and you can consider that k as your choice of k. But then you can do that, and then actually once you get the clusters, you should visually see somehow debug, because it's an unsupervised problem. It's for exploration, so you need to understand what's happening. Okay, the segments should make sense, or the cluster should make sense to you. Yeah.
Just a question of terminology. So when you're measuring the distance from each point to the mean,
these are all vectors. These are all RP. Yeah.
That's k-means
Yeah.
And what would you call the method where instead you're measuring the distance between all points to all other points?
Oh, that was what we were doing here, right?
Yeah, what do you call that?
I didn't call it anything. I mean, because we don't know how to solve this.
That's not a method we use.
Yeah, I just introduced the scoring objective as a way to way to score a clustering assignment. Maybe there is a name, I don't know. Yeah.
How do you get the values for these MQ?
How do I get it if I know C, or you're asking like how do I initialize this whole algorithm? Pick some starting value. Like EM, you had to start. Yeah, it's fine. I mean, yeah, you can pick a random cluster at the beginning. You can just arbitrarily cluster. So first 3 points, first cluster, next 3 points, next cluster. You can do that. I mean, so this is an iterative algorithm. Okay, it's doing something, right? But it's not globally solving. As I said, this problem is actually hard as well. Scoring prime is also hard. Okay, this doesn't have the additional variables, but it's hard. So this iterative procedure of starting from some C naught going to MK, MK naught, MK naught set, it's going from to C1. Okay, these are the iterates. The top indices, top right indices represent iterate. What's the current situation with the C and the M variables. These may not be optimal. It's not the best choices that you would get. So initialization influences where you get to. Okay, just like when you have non-convex problems, then initialization influences where you get to. Okay, these are called local optima. I mean, I think we discussed this when we were talking about gradient boosting, gradient descent. Of course, like for example, logistic regression, it doesn't matter where you start from. As long as you have reasonable whatever parameters of your gradient descent algorithm, you'll get to the best logistic regression model, linear model. Whereas if you use like a neural network or even random forest or even gradient boosted decision trees, where you start, what were the previous trees, and because tree construction is greedy, so that also kind of captures, it's not going to give you an optimal tree as such. These are all shortcuts to get around hard optimization problems. Okay, so there's a slight variation of k-means called k-medioids, where you have data and you have the similarity or dissimilarity measure or metric. I'm just using these names loosely. So some function like d, right, which takes 2 arguments, xi and xj, right? Some function like this. So given these two, you can get a matrix, right? Matrix where each entry is actually d xi xj. Okay, this is n cross n matrix. Okay, let's call this d matrix. Okay, for dissimilarity, where you just given the observations, just compute this pairwise dissimilarity. Okay, remember, for example, this could be so for example, for discrete case, in the sense when the features are categorical, right? So what you may want to use certain prior knowledge to say something about the dissimilar prior knowledge to say how the 2 observation points are different. So for example, some observations cat, some other observations, okay, and some other observations, here's dog, okay, and here it's let's say fox. Okay, just like you remember when we were doing classification, we could say we had this L matrix which would say whether cat is similar to cat, there is no loss. If cat is similar to, if cat is assigned dog, then it's some penalty, and if cat is assigned fox, maybe it's completely bad, so you penalize the model really badly. So similarly, you can say you can use that information in even the dissimilarity function as well. So if the distance between these 2 vectors, okay, cat and with the difference between cat and dog could be small, and difference between cat and fox could be large. Okay, so that's domain knowledge that you can write a script, okay, in the sense that you can write it as like a if then else rule to compute this d function. It doesn't have to be the Euclidean distance type of a thing that we saw in the previous slide. Okay, And once you have that function which computes distances between two vectors, you have the D matrix, and then you give this to the algorithm, which is k medioids. And so what does this algorithm do? It takes this D as the input. It also makes one other change, which is that instead of finding this mk, okay, instead of finding mk, it gets it finds it finds just indices, in the sense that now there is still going to be two steps. Given cluster assignments, I need to find mk's, right? That was the k means, and given mk's, find cluster assignments. The first step, given cluster assignment finding mk's, is slightly modified to get given cluster assignments, okay, given c, find ik's. Okay, what are ik's? They're just going to be the index of a representative point from that cluster. Okay, it's not going to be the mean of points. It's going to be, let's say 1, 2 and 5. I think in the previous example 1, 2 and 5 in the same cluster. Then I don't want to find the mean of these three observations, p dimensional vectors. I want to find a representative point among these three. It could be 0.1, it could be 0.2, or it could be 0.5. Okay, so I'm restricting myself to not compute the mean, but to just give me a representative point, which has to be one of the observations. Okay, and that's because I don't have the points. I don't have the point information. The algorithm is only taking the distance similarity matrix, so it doesn't even know what dimensionality of the observations are. Okay, it just knows what are similar, what are not dissimilar, and it only has the indices of these observations. So all it can optimize for is pick an index which is a representative point for each cluster, and once you have the representative points, find a new cluster assignment by checking for every point from each of these k representative points which one they are closest to. Okay, those are the two steps of the k medioids algorithm.
How do you define the similarity here?
It's the same, right? So this is the you know the D. So you have this data D matrix, okay, n cross n matrix. So 2 points are similar if their number here is small. There's a number, right?
There would be some calculation, right? Like you would be
No calculation. I mean, you just index, look up I and j. If the number is low, they're similar.
So what is this number? Distance or what?
Yeah, that's this dissimilarity measure that I said. Anything you pick. So the algorithm doesn't need to know what you do, what distance measure you use. Okay, there are different distance measures. I didn't want to use some names like Hamming distance. Okay, Hamming distance means how many locations that the entries are different. Okay, so p dimensional vectors, p dimensional observations, how many entries. For example, here maybe all these are the same. All these locations are the same except one entry is different. Then the Hamming distance between these two observations is 1. Okay, so you can use that as a measure difference between two observations, for example. So anyway, it doesn't matter. So once you have D and the data, the distance measure and the data, you compute this matrix D, and that's the input to the algorithm. And the algorithm does the same as before. So it's a for loop over from C, get indices, and given indices, get some new C new, I guess, new cluster assignments. Okay, yeah.
So is an index the actual value of a data point?
No, it's just the index of the data point. I don't know the value of the data points.
So it's where it's located in terms of.
So data points are indexed from 1 to n. So so 1, 2, all the way to n. These are the indices of the data points. Whatever their observations were, I don't have access to them, right? I don't have access to them. I only have the access to this D matrix. Okay, where for I and j, I can find how much similar they are. Okay, so so C, you remember this cluster assignment just saying for this index observation index 1, which cluster does it belong to? Observation index 10, which cluster it belongs to? So once that's it. It doesn't talk about the actual entries. Once you know that, all I'm saying is compute ik by saying what are the points, what are the indices in the first cluster? Maybe point 1, 2, and 5 in my previous running example. If 1, 2, and 5 are in the first cluster, just give me the index of the representative point in this cluster. What is the index of the representative point? Find the minimum. Okay, what is this? Find the minimum over, let's say 1, 2, and 5 are in the first cluster. Okay, these are the points. So minimum over index equal to 1 or 2 or 5 of the distance between that index and the remaining points. Okay, sum over, I guess, remaining points. remaining points, let's say I. Okay. So if I pick, so if my representative point, so here only have 3 choices, right? 1 could be the representative index, 2 could be the representative index, or 5 could be the representative index. So if I pick 1, then what is its distance to 2 and 5? Okay, there will be some distance, right? I can look up in the D matrix and tell you what the total is. Similarly, for 2, I can look up the D matrix and they could be dissimilar. Okay, they could be different numbers and pick the number which is the lowest. If you're using dissimilarity matrix, if you're using similarity matrix, just pick the opposite. Any questions about this part?
So how do you initialize this cluster? Like you take random indexes first and then start computing the indexes. Like you said.
You can start this algorithm by either picking C randomly, cluster assignments randomly, or indices randomly, K indices randomly. Whichever, not just this algorithm, but K means also. I mean, you can pick randomly K vectors, K p-dimensional vectors, and they could be your MKs, and then you can just assign them, and then you get K clusters, and then you get new MKs, new clusters, yeah. I mean, these are iterative algorithms, and they are not expected to, they may not be, they're solving a tough problem, so they will not get to the global optima. I mean, I have not even defined the global optima in this version, but they will not get to global optima.
But in K-means you said that you start with a point and you calculate the distance, right? You initialize the cluster centroids, or maybe random.
What do you mean?
Numbers.
So in this is the for loop, okay, for K-means. Right. You can start with anything. Either you can pick MKs randomly and then just do the 2 steps. Are the 2 steps clear? Yeah. Or you can pick starting from C0, C something. You can do each of the 2 steps. It doesn't matter, but you start with some value for one of the variables.
Yeah, so let's say if I'm starting with MK,
yeah,
I'm making 3 clusters.
K is fixed, okay, in this whole
so it like
3 vectors. You started with 3 vectors, yeah.
Random vectors.
Yeah.
I'll calculate distance of everything and then I'll kind of optimize it.
No. There's nothing complicated going on. If you have MKs, then all you need to do is out of each of my n points, pick the first point. Which of the 3 MKs is it closest to? If it's closest to M1, cluster assignment for the first point is 1. Done. Pick the next point, which of the M1, M2, M3 is closest to. Let's say it's closest to 3, then the cluster assignment of second observation is 3. Done. So you just do it linearly. It's just a linearly check for each observation. That's it. Then you get the C, which for every index, what's the assignment?
But when you are updating points to the clusters, like you said,
what is the other updating remaining? Once you know C, the only thing left is to compute new MKs. New MKs are just, I know what our points I've assigned to them, just average.
Right.
Yeah.
So that you are doing iteratively, right?
Yes, this for loop.
But now in your K-medioids, you
Yeah.
are already using a distance matrix which was already calculated. You are not doing it iteratively, right?
I am changing C and MK. Where is this? I am changing the IKs and the Cs iteratively. Just only the IKs have changed to MKs, okay? I mean, sorry, MKs have changed to IKs. So the difference between K-means and K-medioids is that instead of computing the mean vectors, I'm just picking a representative point. Mean vectors need not be a representative point, okay? For example, 1, 2, and 3, there could be a vector in the center which is like a representative of the 3 points, okay? Here I'm saying just restrict yourself to either 1 or 2 or 3, and for that you don't need to know the vectors themselves. You just need to know the distance matrix or whatever, the similarity matrix.
So when you're referring to the iteration with I, you're just referring to the calculation of the minimum of, let's say.
Yeah, just index. Yeah, which index? So when I said given C, you just need to know remaining points in this. Like let's say this is the first cluster. So if I tell you C, you know what clusters are. That's the end goal. Remember, C is the thing that we care about. Given the cluster, I know what points are there. I just want to find the representative point. That's the step. Once I know the representative points, I can recompute new assignments. That's the second step. And you just keep repeating these steps in tandem. Yeah.
Can you go back to the prior slide?
This slide?
Yeah, that one. So when you add a new data point, you're assigning it to a cluster, and then you're recalculating your mean point for all clusters, or just for that one that it's been added to?
Wait. New data point? I mean, this is a completely bad. I mean, I already have all the endpoints with me. I mean, I have.
When you're assigning one to a cluster.
Oh, okay. So that is this. Yeah. Solve for C is yeah. So solve for C, I have now endpoints. I already know the means of my K clusters, mean vectors. Okay, we just think of them as points. right? In terms of pictures, okay, let's say this is 1, 2 and 5, okay, 3, I don't know what was that, 3, 4 and 6, okay. Either you have the data points and okay, you have the data points and also the clusters. So let's say this is one cluster, okay, first cluster, and this is the second cluster. Just an example. This is my current thinking that this could be clusters. Then what I need to do is find a point which is like in between them, okay, like maybe it's like average of these points, and the average of these 3 points wherever they are, maybe over here, okay. So these are now my M1 and M2, the two centers. Now given M1 and M2, now I have M1 and M2, right. I'm asking, okay, where is 1? Is 1 closest to M1 or M2? 1 is close to M1, let's say. Then it's in the first cluster, okay. That's so I'm going to say this is in the first cluster. Now where is 5? 5 is over here. I don't know which one is closest to, let's say, I don't know, like I want to change the solution, that it's over here close to, okay. So this one changed, right? So cluster assignment. And similarly, where was 3? 3 is over here. I don't know, maybe in the same cluster. Where is 2? 2 is over here. Yeah, I mean, you can just assign things. 6. Yeah, you can just assign things like this.
But I thought you were updating the location of the means after.
Yeah, the crosses, the circled crosses, they are updated in the. This is the step where I'm going from C to MKs, and in this step I'm going from MKs to Cs. C, I mean the assignment of points to clusters. So this would be my new first cluster. This would be my new second cluster.
And as you do the iterations on the first,
No, you just do it alternatively. So you first do first one, second one, again go back to first one, again go back to second one. It's a for loop. Okay, so let's move forward. So there are actually a couple of clustering examples, not examples, there's a couple of clustering techniques that I'm not going to spend time on, which is this notion of hierarchical clustering. Okay, and the way you do it is think of all. So I'm going to do it with one-dimensional example. So let's say these are the points. Okay, clearly, you can just eyeball them as 3 clusters. Okay, so the way I'm gonna do the clustering, and this is going to be called agglomerative. Okay, it's just a word which just means that I'm going to aggregate things. Okay, so the way I'm going to start up with is that every point belongs to its own cluster. Okay, so there are 9 clusters here, and then I'm going to combine clusters. So I'm going to aggregate clusters together. Okay, individual clusters together to create the next level of clusters. Maybe these 2 points are close to each other, then I'll bump them together, and maybe there's a new cluster here, and maybe for this guy there's nothing. Maybe these 2 bumped into together. Okay, and maybe similarly, and then I'll merge them, and maybe merge them. It doesn't have to be like this, but unmerge. So the topmost node is like saying everything belongs to one huge cluster, and at a level, like at this level, I'm saying at this level it doesn't. Okay, this level there are actually 2 points here, this one and this one, and it's just saying there are 2 clusters. One cluster involves 6 points, and the second cluster involves 3 points. It's just an intuitive way. So to start from each cluster being its own point, and then you kind of merge things to create bigger and bigger clusters. At the end of the day, of course, if you merge everything, it's going to be all points, and it's one huge, I guess, trivial or a degenerate cluster. Okay, that's called agglomerative clustering, and you can actually do the opposite. Just like tree construction, you can start with the full bunch of points and start breaking points into parts. Okay, I'm not writing the scoring functions because they are very similar to the previous scoring functions, okay, that we saw. So you break bunch of points into two sets of points, and then for each set of points you again break it into two parts and so on. Okay, so that's called divisive clustering. Yes, in this way. Actually, it's not just this. So before I jump into principal components, which is okay, there's another just remark. There's this. Okay, mixed membership clustering. Okay, so there are various, there are like at least 1,000 or 10,000 algorithms and objectives and techniques to cluster. So mixed membership clustering is just a slightly different beast, saying that a point doesn't have to belong to only one cluster. Okay, an observation can belong to two clusters. Somebody can be simultaneously, a student and a working professional, right? So those, then that observation or their attribute vector should be part of two clusters. So these are mixed membership type of versions. So they require their own different scoring functions and optimization issues and so on. K-means and K-media are not doing this. Neither is the version I presented about hierarchical clustering, but there are other techniques. Okay. So any questions about this part before we jump into principal components? Okay, so what's the use of principal components in unsupervised learning? It's one use is dimensionality reduction. Okay, which means that I have n cross p points, the original X matrix. I want to get to some other matrix X prime, which is n cross q. Okay, it just means that I still have the same number of observations, n observations, but each observation is not p dimensional. Now it's only q dimensional. Let's say q is 5 and p is 50, so you've reduced the dimensionality from 500 to 50 to 5. Okay, why do you care about dimensional reduction? Because in lower dimensions things are better, and we saw curves of dimensionality for k nearest neighbor, right? So if you could do k nearest neighbor on 5 dimensions, it's definitely better for the same number of observations than doing k nearest neighbor in 50 dimensional space. Okay, so dimensionality being low is always good for exploratory analysis, unsupervised learning, or in general any machine learning task. So principal components is a way to do this reduction in a certain way. Okay, so there are many ways to reduce dimensionality. Some of them are, I guess, are non-linear. Principal components is going to be a linear way to reduce dimensions. Okay, it's linear, and we'll see why so pretty soon. Okay, so in this case we'll do that averaging that he was mentioning, where I'm going to assume that this data matrix is such that I have reduced the average observation from every observation. Okay, which means that I've taken the column sum, this is the matrix, right? So each column has some average value, right? The average income, the average pressure level, the average something. So you subtract that number from every entry in that column. Okay, you basically are removing the mean value from the observation matrix. Okay, and then so let's say that's this X matrix already. Then as we said, we want to go from xi to some other vector. Let me call it lambda I. Okay, this is p dimensional. Let's say this is q dimensional and this is p dimensional. Okay, so this is what I want to do, dimensional reduction for only my data points, which are n in number. Okay, now to do so, what I want is a transformation, right? I want a transformation. So I want as I said, it's a linear dimensional reduction technique. So I want a linear transformation. I have a vector which is p dimensional. I have a vector which is q dimensional. So you can imagine the transformation. I'm going to call the transformation actually VQ transpose. Okay, why did I Q is just for the dimensionality of the lower, the Q that I care about. I put a transpose and a V, a capital V. It's just it kind of represents a matrix. Okay, this matrix has to have the dimension of going from. So this is Q cross P. Okay. Q cross P. I mean, taking a P dimensional vector and producing a Q dimensional vector, right? So Q cross P. So why did I use this special symbol? Is because I went from. So this matrix is actually going to be is going to have some special structure. Okay, this matrix will have Q orthogonal rows. Okay, it will have Q orthogonal rows. The VQ transpose will have orthogonal rows, or you can think of VQ having orthogonal columns. When I say orthogonal, it just means that the columns, the bunch of numbers, which are of dimension, these rows are of dimension P. Okay, these P dimensional vectors are orthogonal. Just means that their inner product is 0. Okay, bunch of numbers, multiply them element wise, sum them, it should be 0. That's all orthogonality means. Okay, and pictorially it just means like perpendicular to each other. Think of vectors being perpendicular to each other, then the inner product is 0. Okay. So that's a special property satisfied by VQ transpose or VQ being having orthogonal columns. Then it turns out that if I have Xi, I can do VQ transpose to get to lambda I, which I said is a lower Q dimensional vector. I can also go back from lambda I to Xi tilde. Okay, which is going to be a transformation from a Q dimensional vector to a P dimensional vector. Okay. And because these VQ transpose has orthogonal rows or VQ has orthogonal columns, I can actually use VQ, okay, as a way to go from the Q dimensional space to the P dimensional space. Okay, so this is going to be my preference. Okay, so I want to find VQ. Okay, that's my goal from dimensional reduction perspective. I want to find a VQ which can reduce the dimensionality in a nice way. I haven't even told you what the nice way is, but if I can reduce the dimension, let's say that matrix be represented with this. Let's say it has orthogonal rows. I'm saying that if I had that, then I can also do the opposite transformation. Okay, going from Q to Q dimensional space to P dimensional space. Then I'm calling this thing that I got X tilde. Okay, if these so think of the corner case, right? So if Q was equal to P, okay, Q was equal to P, so P is 10, Q is also 10. Think of VQ as the identity matrix. Okay, they are all orthogonal, by the way. If you just multiply each column or each row of the identity matrix, they multiply and evaluate to 0. So the rows or columns of identity matrix are orthogonal, right? So if Q is equal to P, I'm saying that take a P dimensional vector, multiply with identity, I get the same Xi, which is lambda I. I multiply it again identity, because identity transpose identity is identity, I get Xi. So there is no error, so there is no difference between Xi and Xi tilde. Okay, the whole issue is that I've reduced the dimension and I'm then going back in the dimension, increasing the dimension. There has to be some sort of a loss. Okay, because I had P numbers, I compress them into Q numbers, again I'm coming back to P numbers. There is some loss in numbers, right? So so that kind of tells me what is the criteria. So I want to find a VQ, minimize over VQ, such that over all my data points simultaneously, I want to minimize the reconstruction Xi minus X tilde I. X tilde I is nothing but VQ of lambda I, and lambda is nothing but VQ transpose of Xi. Okay, and let's say distance square for simplicity. All I'm saying is I had to prefer some reduction matrix, right? Some transformation matrix, right? So this is lambda I, and if I project lambda I back to P dimensional space, I get X tilde I, and I want to say the reconstruction between. So I want to reduce the dimensionality such that reduce and get a Q dimensional matrix such that go down and go up, the reconstruction is as low as error is as low as possible. Okay. So that's my criteria for preferring a dimensional reduction matrix. It reduces the dimension but keeps the information about the xi's, all my observation points in the original data or original dimension as much as possible. Okay, it keeps the information in some sort of Euclidean distance sense. Okay, so this is what I want to find, and so this is the objective. Okay, and this is a linear transformation for dimensional reduction. And it turns out that this is a messy problem, right? So if VQ has, think of if it's a variable, decision variable, VQ has a bunch of decision variables, right? All the numbers that I need to fill in to define that matrix. It's getting multiplied by all the numbers transpose. Okay, so it is going to be product of numbers and so on, right? So it's a messy optimization problem. Okay, this is actually a non-convex optimization problem. Okay. Is what? Is not you are asking, saying it's identity? No, it's not. Okay, good question. So what is so this is P cross Q, it's Q cross P. So this is a P cross P matrix, right? It's not identity. Okay, I mean it's not identity for sure, huh? Yeah, it is a square matrix. Of course, it has to be square. It's going from p-dimensional vector to p-dimensional vector. B. Yeah, the columns of VQ are orthogonal. Yes, but it's not identity because P is not equal to Q. If P is equal to Q, yeah, it is identity. I just gave you that example, right? Yes. No, don't worry about properties of orthogonal matrices. I'm not saying that this P cross P matrix is orthogonal. I'm saying that VQ is orthogonal. That's not a square matrix. It's a P cross Q matrix. Okay. I'm just saying that the columns are orthogonal to each other. I mean, there are only Q columns, not all P. Anyway, so this is a non-convex problem, but this is like one of miraculous things happening in, I guess, linear algebra, that you can actually solve this non-convex problem in a very simple, I mean, I wouldn't say very simple. You can solve it in practice in a very simple way by just calling the SVD function. Okay, you call SVD on the data matrix, that X, remember all these Xi's stacked one below the other is the data matrix. So if you call SVD on this X, then you get a bunch of matrices. Okay, I guess what do I use here? U, D, and let's call it V transpose. So you get a bunch of matrices. Okay, you input one matrix, call this function SVD, and it's a polynomial time as an efficient way to compute these three matrices. There is no issue with non-convexity and all that. You get three matrices, and this V here gives you the solution for that optimization problem. Okay, that's a miraculous thing. I call it miraculous, but anyway. So what is SVD? Let me just write down SVD and I'll tell you what so we wanted to find VQ or VQ transpose. Okay, let me not put the transpose, which is P cross Q, right? So basically it's a matrix, the Q of these guys. Okay, Q of these column vectors, they are orthogonal to each other. So let's say there is let's say this is VI and this is VJ column vector, then Vi transpose Vj is 0. That's all it means. Now all I'm saying is if you do an SVD operation on the data matrix, you get an output which is three matrices U, D, and V transpose. This is going to be, so X is n cross P. Okay, so this is n cross I guess P. This is P cross P, and this guy is P cross P. Okay, it just spits out three matrices, and what you do with this V matrix is this has P cross P, right? It's many of them. Okay, let me tell you. So SVD operation produces 3 matrices. Okay, I'll interpret these matrices pretty soon in the next maybe after the break. But before the break, I want to tell you about. So U is an n cross p matrix. Okay, we'll discuss that. It has also some orthogonal properties, but let's not worry about it. So D is actually a diagonal matrix. Okay, it only has what are called the singular values of the matrix X. Okay, there's some diagonal matrices, some entries. These are called singular values, and that's why it's called singular value decomposition. Okay, SVD just represents singular value decomposition. Produces 3 matrices. One of the matrices is diagonal. It has a bunch of singular values. Okay, let me call it sigma 1, sigma 2, all the way to sigma p. Okay, so just think of this diagonal matrix having singular values such that the first singular value is the highest, has the largest magnitude. Okay, so I'm just saying that it's a diagonal matrix with a bunch of numbers. Just reorder the numbers. You are allowed to do that. Okay, if you reorder the numbers, you permute the columns. It's all the same. Okay, permute the columns of U and V such that there is no issue with reordering the singular values. You reorder them such that the sigma 1 magnitude of sigma 1 is greater than magnitude of sigma 2 is greater than magnitude of sigma p. Okay, you can just reorder them. That's fine. In fact, let's assume that the solution that gives you the U, D, and V transpose is such that it is the case. Okay, then you can just pick the Q columns of the V matrix, okay, not the V transpose, or you can think of Q rows of the V transpose matrix. Okay, pick these columns, okay, and call that your VQ. Okay, so the VQ that I was supposed to get from this minimization objective is the same as me calling an SVD function call in Python or R or MATLAB or whatever, and it will be a P cross P matrix. Just drop some of the columns in that matrix. Okay, in the V matrix, drop exactly P minus Q columns, and then you'll get only Q columns. They are all going to be orthogonal. It's just a property of SVD, and that's the best. That's the solution of the previous optimization problem. Okay. Now these guys are orthogonal. As I said, VQ, the columns are orthogonal. They are P length vectors. These P length vectors are called the principal component directions. Okay, so let's call it V1 all the way to VQ. Let me put brackets here. This is VQ. This is the matrix. Okay, this is the matrix, which is P cross Q, and these are all columns. Okay, these are called principal component directions. Okay, and also I forgot to put it in a previous slide, but U, D, V transpose, just multiply the matrices, is equal to X. Okay, n cross P. So that's why it's called decomposition. It's giving a single matrix is a product of 3 matrices. So there's n cross P, P cross P, and P cross P. V itself is P cross P, but you can, yeah. So these are called principal component directions, these guys. Okay, these are vectors in the same space as your data points. Your data points are p dimensional. This is also p dimensional. These are vectors. So and U times D, okay, is this whole thing. U times D is an n cross P matrix. Okay, there's going to be n rows of p dimension. Okay, actually let me, so U, dq, and vq transpose. So I can drop the remember I told you I can drop the columns of V, or essentially rows of V transpose. Then think of going from D, I had all the sigma 1 to sigma p, right, sigma q. Drop these sigmas. Okay, so think of a smaller diagonal matrix. Okay, let me call that dq, and let me put dq there, cross q. Okay, so there are n observations, each one is q length. That q length, vector, right, for the first observation there is a q length vector, that's called principal components. Okay, So that's principal components, and the things coming from V, which are the Q p-dimensional vectors, those are called principal component directions. Okay, I'll discuss more about these two objects.